Yeah, so thank you. As you have heard, my presentation is all about a watermark for machine learning models, and it's called ClearStamp. So first of all, I want to tell you what a watermark in general is. I will make a comparison to the image domain as this becomes more and more important during my talk. So from the image domain, we know how a watermark looks like. It's an overlay of an image, for example. And essentially, we add some data to the image. And we use the same principle for machine learning models. We also add information to those machine learning models to identify the model after a period of time again. So we have the same principle, but first of all, let's talk about why we need to protect those machine learning models with a watermark. So the answer is quite simple. Machine learning models are intellectual property of the model creator. This is due to the costs involved to train a machine learning model. You need to create a data set, you need hardware resources, and of course energy to train the model, and therefore it needs to be protected. We propose ClearStamp, watermarking method that can protect this intellectual property. So against what do we protect the intellectual property of a machine learning model? Of course, an adversary can, for example, steal the model, but he can also buy it and then resell it or do other illegal modifications to the model. So now that we have seen this, let's come back to the watermark protection. We have our image, and we have already seen that we have a visible stamp on the image, and yeah, we added some data there. On the other side, of course, we cannot add a visible stamp to the machine learning model, but we embed some information, unique information, in the model parameters. This is how model watermarking usually is done. For the image domain, if we want to verify the watermark, it's easy. We can just look at the image and see if the watermark is there. For the machine learning model, of course, it's more complicated. You can look at the parameters, but probably you won't recognize anything. So how this is usually done is that you have a watermark model and a secret watermarking key. You feed them into an extraction algorithm that essentially extracts some watermarking data. And these watermarking data are then compared to some ground truth data that are visualized as a secret log here. And they are compared, essentially yielding a similarity score or something, which is then thrown against a threshold. And if the value is above the threshold, we say, okay, the watermark could be found, and otherwise it's unwatermarked. The problems that we have here, or that we want to consider, is that these extracted watermarking data are mostly not human interpretable. So you will find a matrix, a vector, or something like this. And this also involves that you have non-intuitive algorithms. I mean, the algorithms are good, but they are complex, and a person that is not involved into the paper will probably not understand it right away. So we have to put trust in the extraction and verification process, and last but not least, we will mostly have a rigid threshold. So this is a problem, especially against partially removed watermarks. I want to highlight this problem. So if you have a threshold in any metric, some similarity score, and the threshold is 50%, just as an example. If you have a watermark that is embedded with 100% or 85%, no problem, the threshold will work. But if the watermark is removed and yields a metric value of 49%, it's slightly below the threshold. So there you have a problem. Algorithm will say, okay, the watermark is not embedded, but perhaps a human can still observe that the watermark is embedded, if, of course, he can see the watermark, which is not given for machine learning models. You can only see this in the image domain. And this is also the central part of ClearStamp, the method that we propose. We want to have an intuitive algorithm that yields human interpretable data. In fact, we want to create images. And if we have an image as a watermark, you can see here we have a ground truth image and the image yielded by the extraction algorithm. We can replace the decision phase with human inspection. So how do we do that? What is our algorithm to create an image as a watermark, and why is this so intuitive? We use something called transposed training for that. So I will now explain what this transposed training is all about. Everyone knows regular forward training. We call it forward training, which is regular machine learning training. You have some samples from a data set, you feed them into the model, you get the predictions, compare them to the labels by using a loss function, for example, cross entropy. In transposed training, we use a model from the reverse side. So we create a prediction-like vector, which has the same format than a regular model prediction here. and feed it into the model. And as a result, as we feed it from the reverse side, we get an input-like image as an output. And this image relates to a secret watermarking key, which is also an image. So we have now two images. This image will be slightly different than that, and therefore we have a loss function that will adjust it that it is the same thing. So we have forward training, regular predictions, a main task, and transposed training from the reverse side, where we can input our watermark. So, of course, we can embed multiple keys here, and we will share the parameters, so both of these things will be in the same model. The details for doing the transposed training has to be done on a layer-wise basis, so each layer has to be reversed from the transposed side. Some layers, like linear layers and batch normalization layers, we could come up with formulas that just reverse the action. For other layers, like convolutional, pooling layers, there are works that care about exactly this problem, how to reverse this action. And we use these works here, and if you want to see more details about that, you can go to the paper. For now, consider that it's possible to create a transposed model. So what we then have to do is we have to entangle the parameters within, entangle the watermark within all parameters, because we face this situation that we train the watermark into the model, and the watermark is essentially embedded into a shortcut. So just some parameters are watermarked. We do this by adding artificial dropout layers to the transposed model architecture, and with this we can distribute the watermark over all parameters. These dropout layers do not have effect to the regular training or during inference. Beside that, we also care about that the prediction-like vector here is in the same value range than the regular predictions, and that the images here are in regular image values. So we have three things. We have the dropout layers, and we care that the input and the output are in regular value ranges. So with this, we can entangle the parameters of the watermark in all parameters. So now that you know what transposed training is, I will tell you the workflow of ClearStamp. So how do we embed the watermark into the model? First, we only train a watermark into the model. We call this watermark hardening. So we have a model that has a watermark embedded but has no main task. Afterwards, when this is done, we have a constrained training phase where we train the main task, and we keep the watermarking behavior in the transposed training as a constraint during training. So we train the main task, and the watermark will survive this. Afterwards, we can sell our model, and an adversary might change the model. And to check if there's a copyright infringement, we can then feed the key into the model from the reverse side. We get an image, and we can compare it to the ground truth. We can do this by human observation. So after you've seen the workflow of ClearStamp, I will now show you some results. I will show you the results with the MNIST dataset, since it's easy to understand. This image here is our watermarking image. We decided for image with ABCD on it. This is the ground truth, and here is a prediction-like vector. Just to visualize it, there are, since we have 10 classes, 10 values. So when you have an untrained model, you have no accuracy in the model, 10%, it's a naive model, and the extracted watermark looks like noise. When we then train a regular model without watermarking, you can see that there's high accuracy, and we still have a lot of noise, so there's no watermark embedded. If we only embed the watermark, the situation is different. You can see the watermark now if we extract it, but the accuracy is very low because we trained no main task. If we then apply ClearStamp correctly, you can see that the accuracy is high and the watermark is there. And the situation also doesn't change if you embed more watermarking keys. So we don't only have one picture, but we used multiple pictures. So here you can see different watermarks that we tested. So overall, the system is okay. Now the adversary can manipulate our watermark model. The first thing that we tried is fine-tuning. We fine-tuned with different learning rates, same learning rate, 10% of the learning rate, and also on unseen data. And the results are always the same. The adversary has good performance in fine-tuning, so he achieved his goal, but he could not extract the watermark with fine-tuning. Then we used pruning. There, the situation looks different. So the adversary is able to more or less remove the watermark, so you can barely see the ABCD anymore. But perhaps you might notice that he sacrifices a lot of accuracy here. So in fact, we have a clear correlation between the quality of the model and the quality of the watermark. And here we can see that our entanglement with the dropout layers and the value ranges, that this worked. So if we prune the model, you also sacrifice a lot of accuracy. If we then combine these two methods, it's called fine pruning, the adversary has quite good chance to to partially remove the watermark while having a good accuracy. But the thing here is, a rigid threshold might not detect this now, this watermark. But as a human, you can clearly see that the watermark is still embedded, especially if you compare it to the unwatermarked model. So for this, you can clearly see, okay, this is ABCD here. Then the next thing that we did is to erase the watermark with the same method how we embedded the original watermark. For example, embedding a black image onto it or trying to remove the watermark with the same method. You can see here that the adversary can be successful in removing the watermark with such a method. And especially here you can see the results if the adversary tries to embed a noise image as a watermark. But we can see the same thing again. He sacrifices accuracy similar to the pruning approach. So we were not successful in removing the watermark with any of these three methods and keeping the accuracy high, which is exactly the thing that we want. Regarding the capacity of the watermark, we made an experiment using the MIT license text, which is around 8,000 bits. And we encoded them using .code, such that we have images, and we could embed the MIT license text in a ResNet 18 model and could extract it with a bit error rate of around 6%. So the capacity of this thing is quite high. The runtime, we have a one-time effort for the hardening phase, so the first phase of ClearStamp, which of course takes some time, but it's not too much. The training increased around 40% for a ResNet model. This is clear since we have an additional loss function for the backward or the transposed training. The extraction, however, is quite fast. It's just an inference. So we also evaluated our system in different dataset and model scenarios, also with a dataset, we used Cypher 10 as a first dataset and then fine-tuned on Cypher 100 and then fine-tuned on Cypher 10. But you can see overall that the watermark is always visible and that we could clearly detect the presence of the watermark. So we can say our system is model and dataset independent. And as a conclusion, I can say that copyright infringement of machine learning models is a real threat and that therefore we watermark our models. The existing approaches are often non-intuitive, have rigid thresholds, and especially against partially removed watermarks, they are not optimal. And therefore, we proposed ClearStamp, a method using transposed training to generate a human visible watermark, which has not been done so far. So now I'm happy to take your questions. Thank you.